So we're going to start a new chapter today, chapter 30. It's about Faraday's law of induction, and we will speak about Lenz's law also, the EMF that induced by motion and changing magnetic field flux, and the general form of Faraday's law. So we have 4 sections to cover. So let me first of all show you a demo.
Whether you're new to the world or connected.
Increase the volume to the max.
We're going to have a look at Faraday's law of induction. For this demonstration, we've got a ring which consists of many turns of copper wire. Regrettably, it's covered with tape, so they're not visible. It was known that when electricity went around a conductor, it produced magnetism. People had made electromagnets before Michael Faraday came along. If the magnet sits stationary inside the coil of wire, no electricity is made, and we can see that the meter needle is not moving. If the magnet is moved, the magnetic field within the coil of wire changes. And it is this changing magnetism that induces electricity. This is what Michael Faraday discovered. And notice that by moving the magnet in different directions, we produce electricity in either the forward or the backward direction. We can illustrate this with a bar magnet. The magnetic field of a bar magnet points away from the North Pole. And so we could imagine a series of magnetic lines coming from the north end with arrowheads pointing away from the North Pole and toward the South Pole. If I move that magnet into this conducting coil, I am increasing the number of magnetic lines that point in the direction I'm moving. So this is the reason that when I move a magnet in and out of an electric coil, I see my meter change directions and show me electricity moving first in one direction and then in the other. Another way to look at Faraday's law would be to produce electricity by induction and then use it. And so we've got an apparatus in which we have 2 coils, each of them placed vertically on the table. And above each coil is a magnet hanging from a spring. The magnets and springs are identical. If I move one of those magnets in and out of the coil, it will induce electricity.
So note he's introducing electricity.
Second, we'll take a small battery and connect it to the second coil and see that when we put electricity into the coil, it produces a magnetic effect on the hanging magnet, and the hanging magnet moves vertically. So now we'll connect the 2 coils with wires and start bouncing the first magnet so it moves up and down at its natural frequency, producing electricity at that frequency.
So
the motion of the first magnet
coil
will be translated to the second magnet electrically, and we'll see the second magnet begin to move at the same rate as the first magnet because we are inducing electricity in the coil. The magnet doesn't just sit there, the magnet has to move.
All right. Okay. So this is actually a very nice illustration of Faraday's law, and so until now we have looked at different effects.
Whether you're new to the...
Oops.
This is a demonstration of eddy currents. I have...
Okay. We have seen different effects. So let me summarize what we have seen so far. All right. So far, we have seen that if we have a charge, if we have a charge moving, let's assume a positive charge that is moving in a magnetic field, it will experience a force. So it will experience a force that is perpendicular to the two. All right. So we know that the magnetic field can exert a magnetic force on a moving charge. If it's not moving, it does not exert. If it starts moving, it exerts a force. Okay. Then we determined in the previous chapter that the electric charge, when it moves, or current, so when a charge moves, or a current, so that when a charge moves, positive charge moves, it's a current, so we can say this is a current I. Here, it generates a magnetic field, and the magnetic field makes a circle around it. So this is, it induces, so if the current is like this, the magnetic field, so there will be an induced, so be induced. Okay, so what else did we see? We've seen the effect of magnetic force. All right, now this is a new observation. Well, it's not new. I mean, Faraday discovered this centuries ago. Is that actually the changing magnetic field can induce a current? So if we have a magnetic field, let's say a magnetic field that is changing, okay, and if there is a sitting charge, okay, the changing magnetic field will cause the charge to move, because that's what we have seen in the current and the previous illustration. We have seen when we move a permanent magnet into or out of a coil, we induce a current in that coil. So the coil originally, it has a conductor, so it has free charges. They can move, but normally they are not moving too much. They are moving randomly. Okay. As soon as you try to move a magnet in or out, and you change the magnetic flux through this coil, the charges will move, and it will move only temporarily, as long as the magnetic field is changing. If you stop the change in the magnetic field, if this is not changing, it will not move. Okay, so this is a new observation. When Faraday discovered this was a big invention, because this actually led to other discoveries later on, applying Faraday's principle. Okay, so in fact, this concept of induction is the basis of electric generators and electric motors. All right, so let me go to the right. So what is an electric motor? Okay, an electric motor, if you have a coil like this or a loop, this is a blue loop here. Okay, so this is a loop, and if you pass a current through it, so there will be a current. So let's assume this is a current here. Okay, and so the current will be in the opposite direction. If you have a permanent magnet, this is, let's assume, north and south, for example. Okay, between them, the magnetic field will apply a force. Remember, when we have a current flowing and the magnetic field, the wire, the wire will experience a force. So, in other words, there will be, let's assume there will be a force like this, and a force here in the opposite direction. So it will apply a torque on this loop, and so this torque causes it to rotate. And that's the principle. So we're converting electricity, or a current, we're converting an electric current here to rotational motion. This is the principle of the electric motor. And you pass electricity and you generate mechanical energy. So in this case, an energy of rotation. So the electric motor, which is almost everywhere now, okay. Also the electric generator. So this one is using the principle that we studied in chapter 27. Because in chapter 27 we said if a current is flowing through a wire, it will experience a force. So we can convert this current into mechanical energy, and we can induce rotation. So that's the principle of the electric motor. The principle of induction is the opposite. So here, for example, we just rotate this coil here. It does not originally have a current. There is no current flowing. What we do, we have a permanent magnet, So we have, let's say, the north and the south. Let's, for example, north and south of a permanent magnet. And we start rotating this coil mechanically. All right? As we start rotating this coil mechanically, the flux, the magnetic flux through it is changing. This changing magnetic flux actually will induce a current in this coil. So this current here is induced. It was not originally there. There is no battery to cause a current to flow, okay? But there is only a magnetic field and mechanical motion that is rotating this loop, and the rotation of this loop will generate a current. This is the principle of hydraulic generation of electricity. So what you have water falling, and you have a turbine. The waterfall causes something to turn, the turbine to turn, and what you have this. So you have coils, okay? As they are rotating due to the rotation motion coming from the fall of the water, you are generating electricity. So this is what we call the generator. Okay. So here we are converting mechanical energy, mechanical motion, into electric energy, into electricity. So these are two very important devices that we depend on these days. You can see electric motors in many devices, electric generators are used to generate electricity and so on. Okay, so how did all of this start? Okay, Michael Faraday did an experiment and he observed this. So let me go to the presentation mode. Okay, so what he did, he noticed that if you bring a magnet, just the experiment we have seen in the video, if you bring a magnet close to a loop, so this is a magnet here. First of all, if you don't move it at all, if you don't move the magnet this way or this way, there is no motion. There is no electricity induced in this coil. This is a meter. So he must have used a very primitive meter at that time to measure the current in a wire. Okay, so if you move the magnet, this is the north pole of the magnet, this is a permanent magnet, and this is the south pole. If you move it close to this, you can see these are the magnetic field lines. Okay, the interesting thing is we notice a current flowing in this direction, and it gives us a negative current, meaning it's moving from you will see later why it's in this direction. Okay. However, if you move it away, here we're moving the magnet away, we induce a current of the opposite polarity. As you have seen in the video, as he moves in the north pole, he gets the needed to deflect on one side. As he moves it out, it deflects from the other side. So if you move in and out, you start having currents, an oscillating current, AC current, okay, by just the movement of the magnet, of the permanent magnet in and outside of this loop. So this was his observation, and obviously the current appears only if there is a relative motion between the loop and the magnet. Otherwise there will be no induced current. Okay, and we will see why. Okay, so this is summarizing the observation that we have seen the video. So here we are showing a loop, and the loop is connected to an ammeter that measures the current. If the permanent magnet is not moving, we don't see any current. But as soon, we also notice that if you move the south pole instead of the north pole, the current will change in the opposite direction. So if you move the north pole into the coil, you get deflection to the negative side. If you bring the south pole instead of the north pole, you get direct deflection on the opposite side. So this is another observation, and we will see later on why. Okay, so same thing, if you pull the south pole away from the loop, you get a current in the opposite direction. So a current appears only if there is relative motion between the loop and the permanent magnet. Okay. Now, the other observation they found, or Faraday, is that it depends on how fast you move. So, if you move the south pole into the coil with a slow motion, you get a small value of the current. But if you move it, so this is here, you get, for example, the ammeter will measure a certain current. But if you move it faster, you'll get a stronger current. So the larger current. So it's not only dependent on the change of the magnetic field, it also depends on how fast you change the magnetic field. The faster you change the magnetic field, the stronger the current. And that's why when we use the electric generators and the the dams, we want water to be flowing at a high rate in order to induce a fast rotation, and the fast rotation will give us very strong currents and voltages. Okay, so faster motion produces larger current. This is another observation. Okay, we said that bringing the south pole will induce deflection on one side, bringing the north pole to the loop will cause the current to deflect on the other side. So all of these observations we have to try to interpret them. And that's where the role of the physicist and the mathematician comes in order to convert these experimental observations into equations and into models that we can explain what is going on. Okay? So, if the magnet is reversed, the current is also reversed, meaning if you reverse from the south to the north pole, you get different deflection in the current. Okay? So, this is what we call induction. Basically, we are inducing a current by the movement of a magnet, and what is really happening, we are changing the magnetic flux. Remember last chapter, we defined the magnetic flux, and we said the flux is the integral of B dotted with TA. Okay? So, the flux through this loop is changing. And as you change the flux, it induces the current. And we will see the equation later on. Okay, so this is what we call an induced current. Okay? This induced current, as if there is a battery, as if for a short moment you're introducing a battery. When in reality there is no battery. That's why we call it induced EMF. Remember, we used electromotive force to refer to the battery, and remember I said this is not a good name, and this is a very old name, but it is as if you are temporarily putting a battery in this loop when there is really no battery. So that's why we call it induced EMF, and it is this induced EMF or voltage that produces a current in the loop. So this is the work done per unit charge to produce an induced current, and so the process gives us a current and the EMF. Okay, so if we actually know the resistance of this loop R, okay, the induced EMF is going to be equal to the resistance times the current that is induced. So this is induced EMF and this is induced current by just moving in and out the permanent magnet in the loop. Okay, so here is another experiment. This is another observation. Okay, so here what do we have? We have a battery, and the battery is connected to a coil. Okay, and there is an iron. This is and the iron, we have a secondary coil. So the secondary and the primary coil are not connected; they are separate circuits. And what we do, we connect the secondary coil to an ammeter to measure the current. And what we notice is the following: as you close the switch, you see a temporary current in the secondary coil. So what will happen is when you close the switch, the current that is flowing through this coil, through this solenoid, will induce a magnetic field. So the magnetic field will change, B will change. Okay, let's assume it will increase. this magnetic field will induce a current in the secondary coil. So, and you can measure it. But you can only see it when there is a switching. In other words, before the switch is closed and long after the switch is closed, you don't see a current. You only see an induced current as you are closing the switch. Why? Because at that time, you are changing the magnetic flux through the secondary coil. This is actually the principle of a transformer. A transformer, we will see later on. So basically, you have a primary coil and a secondary coil. They are not connected, but changing the voltage in the primary coil will cause a change in the voltage in the secondary and current in the secondary coil, even though they are not connected. And the reason it's called a transformer, by controlling the number of turns here and the number of turns here, we can get higher voltage. For example, you can have 10 volts here and 100 volts here, or vice versa. You can also reduce the voltage from 100 volts to 10 volts, and so on. So that's why it's called a transformer. So in your certain devices, you connect it to the outlet. It has, let's say, 220 volts, and your device works only on 5 volts. So you need a transformer in order to bring the voltage down from 220 to, let's say, 5 volts or 10 volts. For that, you need a transformer. So this is here. It's based on also the same principle of induction. As the voltage is changing, and the current is changing in the primary coil, the magnetic field is changing. This magnetic field changing will induce a current in the secondary coil. Okay, so this is transformation of energy from one side, from the primary coil to the secondary coil. So a current appears momentarily only if the switch is closed or opened. Okay, so this is illustrating the same thing. So here we have a circuit on the black color. Okay, the switch now is open. Okay, the current is 0. The current meaning through the blue loop is 0. Okay, as soon as you close the switch, okay, so no current here. As soon as you close the switch, you will notice a current will appear in the blue circuit, or in the loop that is made by in blue. Okay, so this is induced, and it only appears when we close the switch. After you close the switch, it will go down, it will go back to 0, because after that there is no changing of magnetic flux. What's happening here is we have a current, so the current is flowing here. Okay, so this is current flowing through this current is going to produce a magnetic field. So if we use the magnetic field, so the magnetic field here, B, will increase as we switch the close, as we close the switch. Okay, as we close the switch, we are inducing a magnetic field. Okay, this magnetic field changing will induce a current in this loop. We can call it a secondary loop. So here we have a primary loop and a secondary loop. Okay. What's interesting is that the current that is induced in this coil here, as is shown here, if you look at the direction of the magnetic field, if you put your thumb in the direction of the current and you swing, you notice that it's in the opposite direction of the original magnetic field. So what we observe, let me change the color. We observe that this one here of the magnetic field that is induced is opposed to the changing magnetic field that is existing. In other words, in the secondary coil, the induced EMF and current opposes the change. Because this here, it's increasing the magnetic field in this direction, it generates a magnetic field in the opposite direction. It doesn't like the change. Like many things, nature, they want to be in a stable condition. They oppose change. So here, if you are trying to induce change in the magnetic field, this induced current is opposed to that change. And we will see that in many other examples. Okay? So here we start with the switch closed, and now we are doing the opposite. We are opening the switch. Okay? So originally we have a current, so the current is in this direction. Okay? So the magnetic field is in this direction, except the magnetic field is decreasing because we are going to open the switch. So here, when we open the switch, let me show you. So now when we open the switch, this magnetic field is disappearing. It's going down to zero during the switching process. Okay? So the induced current that we observe in this case, so this is the induced current. Notice now the current is in this direction. So if we follow the current, this is the current, the induced current, the induced current is like this. Okay, so this is I induced. Okay, now let's try to determine what is the direction of the magnetic field. Okay, so you point your thumb like this and you swing with your 4 fingers. You find it's generating magnetic field in the same direction. Why? It's opposing the change, because this magnetic field is decreasing. It does not like the change. So it's generating a magnetic field to oppose the change. This is what we call Lenz's law. The induced EMF and the induced current, the EMF and current are connected together. They oppose the change in the magnetic field. So if the magnetic field is decreasing, it will generate a magnetic field in the same direction because it does not like the decrease. But if the magnetic field is increasing, it will generate a magnetic field in the opposite direction. It opposes the change. So always the induced EMF and the induced current are opposing the change of the magnetic flux. I'm not saying opposing the direction of the magnetic flux. I'm saying opposing the change in magnetic flux. Notice that the induced here, the induced magnetic field is in the same direction. In the previous case, we've seen it's in the opposite direction because the magnetic field was increasing. It generated a magnetic field in the opposite direction because it opposes the change. Now, the magnetic field here is decreasing. It's in this direction. So it generates a magnetic field in the same direction to keep it constant. It doesn't like the change of magnetic flux. So very interesting. Okay. So the current will appear in the coil and it will oppose the change. All right. So these are the two observations. We have seen observation due to a permanent magnet in a loop moving in and out will generate current or induced EMF or induced current. And we have seen you can also do it with an electric circuit. You don't have to have a permanent magnet. So here, with this circuit, you are basically generating a magnetic field that you can control. You switch on and off. Remember, the current flowing generates a magnetic field. That's what we've seen in chapter 29. Okay? So, if you make any changes here, or if this is, for example, instead of DC battery, if you have an AC current, you will induce current and voltage in the secondary loop. All right, so here is two. So you can have the source either a changing magnetic field due to a permanent magnet, or you can have a changing magnetic field due to a current flowing through a wire. We have seen that a current flowing through a wire generates a magnetic field. Okay? So Faraday's law says an EMF induced in a loop when the number of magnetic field lines that passes through the loop is changing, meaning the flux is changing, the magnetic flux is changing. The value of the induced EMF is determined by the rate at which the number of magnetic field lines change. How can we convert that mathematically? Okay, we want to write an equation. So here we have a flux that is changing, magnetic flux, and we have an induced EMF. What do you think is the equation between them? The derivative, correct? That's Very correct. Thank you. So we can write the derivative. What is missing? There is something missing. We said the induced EMF opposes the change. Negative sign. So that's how you convert physics observation into mathematical equations. You observe experimentally something, and you say, okay, how can I describe this mathematically? All right? So you need a minus sign, because this induced EMF is always opposing the change in the magnetic flux through the coil or whatever you're having. Okay? So the magnetic field lines, let's say, for example, you're bringing the north pole. Remember, the magnetic field lines are like this. They are moving. So here, if you bring the north pole to this, you are increasing the number of magnetic field lines into this loop. Okay? And when you are increasing it, the current it will generate is going to be in the opposite direction. This is a negative current. Okay? It's opposing this increase. All right? Now, if we move it away, the number of field lines, and hence the magnetic flux, is decreasing. When the magnetic flux is decreasing, it will oppose this change. So it will generate a current in the opposite direction. Okay? So, same thing here. So we already explained this already. Okay, so this is the formula for the flux. We have seen this in the previous chapter. The flux is the integral of B dotted with dA. And if B and A are, if you have a simple area, dA and B, and you have, you know the angle, you can write that the flux is going to be equal BA cosine the angle between them, cosine theta. Okay? So we have seen this in the previous chapter, and we have seen the special case of perpendicular. So this is repeated from the previous presentation, so we don't need to repeat it. Now this is the formula. Michael Faraday is a physicist and chemist. He lived in the early 1800s, and one of his greatest experimental scientists. His many contributions to the study of electricity include the invention of the electric motor, the electric generator, so all of these are credited to him, the transformer, as well as the discovery of electromagnetic induction. So great contribution. So his law says the magnitude of the EMF induced in a conducting loop is equal to the rate at which the magnetic flux through the loop changes with time, with a negative sign. This negative sign is credited to Lenz. So he said the induced EMF is always opposing the change. So that's why we must have a negative sign. So this is the induced EMF. It's minus the derivative of the magnetic flux with respect of time. Okay? So this is the model. All right? Now, so if you have one loop and you change, for example, the magnetic flux through this loop, so you change the flux, all right? We can write that the EMF, the induced, is minus the derivative of the flux with respect of time. This is for a single loop. If now you make a second loop, you do a second loop, this becomes minus 2, the derivative of the flux with respect of time. As if every loop is generating an EMF, a battery. Okay? And these batteries are now connected in series, so the voltages are adding. So the induced EMF is the sum of the EMFs. So you have one loop, generates one EMF, one induced voltage and current. You have a second loop, that's a second EMF, a third loop, and so on. So if we have n loops, if we have a coil that had n loops, and you change the magnetic field through it, you generate n times the EMF of a single loop. And this is what we have in the, so here we have loop n terms, so this is a coil, and the induced EMF in this case, so it should be epsilon, okay, it's minus n times, where n is the number of coils or the number of loops in this solenoid. Okay, so the EMF in this case is for a single loop is minus d phi dt, or is but if it's you have n loops, the total EMF is a sum of the individual induced EMFs. Okay, so that means you can generate very good voltage from a single loop. Maybe you can generate a few millivolts. A second loop, you double that. A third loop, you triple that, and so on. And if you keep doing that, you can generate quite a significant voltage. So here, the magnetic flux changing can generate very significant voltage that you can use in your everyday devices or circuits. Okay, so let's assume we have this loop and we have this magnetic flux. Okay, and let's assume there is an angle of theta between the magnetic field vector and between the area vector. So this is the area vector. Let's assume this is the area vector here. Okay, the question is, how can you induce EMF? What can you change in this case in order to induce EMF in this loop? We have, this is the equation. So the flux is, in this case, is BA cosine theta. Okay, the induced EMF is given by Faraday's law. It's minus the derivative of the flux with respect of time, which is minus the derivative of the flux, which is BA cosine theta. The question is, how can we, the n is missing, change the magnetic flux through this loop? What can we do? Okay, yes, what can we do? Change what? So, okay, we can change the magnetic field. What else? We can, for example, have motion. For example, we can change the angle theta. If I rotate this loop, I'm changing theta. If I'm changing theta, I'm changing the flux. Then if I'm changing the flux, I induce EMF. What else? The area, we can change the area, clearly. So if you have this is something that you can deform, by changing the area, you are going to be changing the flux. You can see here that the area is part of the equation. So either you change the magnetic field, you induce an EMF, or you change the area, you induce an EMF, or you change the angle theta and you induce an EMF. All of these can be basis of devices, of new devices. So by changing, for example, by changing the angle theta, that's the principle of the electric generator. Or yes, the electric generator. So you're mechanically rotating, for example, this loop here, and by rotating this loop here, you're changing the flux, because you're changing the angle theta, you're changing the flux, you induce an EMF. Okay, so very interesting. So we can either change the magnetic field, we can change the area enclosed in the loop, or we can change the angle theta between the normal to the loop, and so all of these, or you can do a combination of these. You can combine, you change both the magnetic flux, change both the magnetic field and the rotation, for example. So you can generate stronger or weaker EMF depending on which ways they are changing. Okay, so I'm going to mention only a couple of devices that use this principle of induced EMF. Okay, the first one is what we call the ground fault circuit interrupter or breaker, circuit breaker. Okay, so imagine you have the outlet connected here in your house. Okay, and so you have a device here. There is a current going to your device to energize it, to give it power. Then there is a current coming back from your device. In normal condition, the current moving out and into this loop. So this is here a loop, okay, and this is a coil, okay, and the coil controls a switch. Okay, so there is a switch. So originally, if the current in and out are equal, there is no induced magnetic field here, because so one induces magnetic field in one direction and the other one in the opposite direction. So they will oppose each other. So you don't have induced magnetic field in this coil. However, if something wrong happens with the instrument and the amount of current decreases, the current coming back because it's getting lost somewhere, there is a short, for example, it's getting lost somewhere, this current will be less than this current, and then now the magnetic flux is not going to be zero and it's going to be changing. As soon as the magnetic flux changes, this here will detect the magnetic field and it will trip the switch and it will open the circuit. So it will stop the current from flowing. So this switch here will stop all the current flowing into the device. So this is a safety circuit and it's called the ground fault circuit interrupter, and it's based on magnetic induction of current. So you here to induce magnetic field. The magnetic field induces an EMF. The EMF controls this switch, close it or yes, usually or open it if there is a problem. Okay. The other instrument is the electric guitar. So the electric guitar has what we call a pickup coil. Okay. These are the strings that the musician hits. So this will vibrate. Okay. This is magnetized due to the permanent magnet here. So as this vibrates, it changes the magnetic field in this coil. So here you can say this is magnetized, so it will be south and north pole. It's moving in and out. As it moves in and out, as it's vibrating, it changes the magnetic field in this coil, and this is picked up by an amplifier. So there is a circuit because you are changing, you're inducing an EMF, a current. Okay, so the EMF generates a current, voltage generates current. Okay, this voltage goes to an amplifier and it goes to your speaker. So as the electric guitar player is hitting the strings, the pickup coil convert mechanical vibration into electrical signal. So this is magnetic field flux changing through the coil. It induces an EMF. This EMF is what you hear and what you convert. Obviously, the amplifier itself, not the amplifier, the speaker, converts electrical signal into mechanical signal. You know the what is it called, the discs of the speaker, they move in and out due to an electrical signal variation. And that generates sound waves that we hear. Okay? So you have another conversion later on from electric to mechanical motion of the speaker. I forgot what they call them, diaphragms. All right, so this is another instrument that is based on electric induction. All right, so let me see if you understand what I just have explained, mathematically at least. Here we have the magnetic field changing versus time. So first of all, it's constant here, it decreases, then it's constant, then it decreases, and so on. Okay, the question is the following, and I did not prepare a Kahoot for this. Rank the time intervals according to the magnitude of the EMF induced in a conducting loop perpendicular to B. Okay, so imagine we have a loop. Okay, this is the magnetic field B. All right, and this is how the magnetic field is changing. Okay, we want you to rank these the induced EMFs. So because B can be changing, we want to rank the induced EMF in these different sections: A, B, C. Obviously, D and E should be the same. Okay, so here choose between A, greatest first, B, C, or D. I'll give you 20 seconds or 30 seconds. Yes. Okay, A, B, and the same. So ignore one of them. Ignore B. So have A, C, and D. Sorry for the mistake. All right. What do you think? Okay, so let me give you a little bit more time. Think. Okay, so I will just say A, C, or D, because A and D are the same. Who says it's A? Who says it's C? C. Okay. Who says it's D? So it looks like we have a much larger number of C. So let's look at this. All right. All right. So what do we have? We have the EMF is minus the derivative of the flux with respect of time. All right. So what is the EMF for A? Here, minus the derivative of B with respect BA with respect of time. It's 0 because the flux, the magnetic field is not changing. So for the section A, it's 0. Okay. Whoa. What is it for B? So for B, we have the steepest slope. So minus the derivative of BA with respect of time. So let me call this slope S1. Okay. For EC, same thing, it's 0 because the magnetic flux is not changing. Okay. And for D and E, the slope is the same. This slope here is the same. So ED is equal to E, and it's minus the derivative of the B times A with respect of time. But notice the slope is smaller. Okay. So are they asking about the magnitude? Yes, they are asking about the magnitude. Which one has the highest magnitude? So it has to be B. This one has the highest magnitude because it's the steepest slope. Then we have D and E. Then at the end we have E and C that are equal. So the correct answer is C. All right, so I will stop here. We did not advance much, but it's okay. So tomorrow we will continue on